Corrosion modeling can typically be divided into two different branches, being modeling of the corrosion processes and modeling of corrosion protection systems. We do this in context of given geometries and material parameters. Both branches have the same fundamental governing equations, but usually some simplifications can be made when modeling corrosion protection systems. We have specialized functionality for this that will be covered in details in other sections of the training course. And this session will cover the more fundamental functionality for galvanic corrosion processes. COMSOL Multiphysics and the Corrosion Module can be applied to model corrosion protection systems such as impressed current cathodic protection with sacrificial anodes, anodic protection, for example applying a small passivating current, or internal cathodic protection in pipelines, and more. When modeling corrosion processes, all types of galvanic corrosion processes can be modeled, such as pitting corrosion, crevice corrosion, atmospheric corrosion, corrosion caused by stray currents, and even stress-induced corrosion cracking by use of multiphysics capabilities of the software. The phenomena that are described by the governing fundamental equations are mass, current and charge conservation in the electrolyte, current conservation in metals, electrokinetics and thermodynamics from built-in database or user-defined expressions, arbitrary number of reactions on each surface, and you can also model deformed surfaces due to corrosion. These phenomena and equations are contained by the interfaces that you can select for your application when using COMSOL Multiphysics, such as with the cathodic protection interface, primary, secondary and tertiary current distribution, corroding surfaces and growing calculus filled with fixed or deformed geometry using moving mesh functionality. Basically, when modeling corrosion or protection systems, you model the transport of anions and cations in an electrolyte or electrons in the electrode. This is done by including the equations for mass transport, charge transport and ensuring charge neutrality and mass conservation. For the electrochemical reactions occurring on the anode and cathode, you can have multiple reactions. The charge transfer reaction rate and current density are related to Faraday's law. Polarization curves, they show the current density as a function of electrode potential, and these expressions are given by, for example, Butler-Volmer and Toffler equations, or user-defined expressions, or you can pick it from a library of materials that we have included in the module. Following this, you may have deposition or dissolution of films and metals, and this can be handled by using a moving mesh or other types of equations such as level set or phase field. And this will be shown in details in other sections of the course. This is a view of all the physics interfaces available within the Corrosion Module. It includes specialized interfaces for current and charge transport as well as transport of mass. You may also couple this to fluid flow, heat transfer and other physics represented in your real-world application. On a corroding surface, you may couple electrode reactions to surface species, as well as couple the deposition of films to surface species. You may model both stationary and time-dependent or transient studies. In the next section, we will dive into the equations that we solve when we work with corrosion-related modeling. In the electrolyte, we have conduction of ions, whereas in a conductor we have transport of electrons. In electrochemistry, we're interested in materials that conduct current by transport of ions and how chemical equilibria together with the electrochemical reactions on the boundaries interact with the electrolyte. For example, if we dissolve sodium chloride in water, the chloride ions will migrate towards the anode and the sodium ions towards the cathode. The positive direction of current is chosen to be from anode to cathode. At the boundaries, the chemical reactions proceed at the electrolyte interface with electrolysis. Across this interface is a potential difference, And the position of equilibrium and the current exchange depend on this potential difference. Faraday's law states that the current is proportional to the flux of reacting material at the surface. The net flux of material A is into the surface, and the net flux of ion B is out of the surface. If we break this down into an equation for the flux of ions, we get this diffusion convection migration equation for the flux. So the flux N is given by this diffusivity term and the concentration of ion. Then we have the convection term, and then we have the migration term. Then if we have several species, the current density is the sum of all these fluxes. And as you can see, you have the sum of the charges as a term connected to the convection part. In most cases, we can assume that you have local electroneutrality. That means that the sum of charges is zero, and you can neglect this convective term for the current density. So this is the electroneutrality equation, and you can also simplify it even more if you assume that you have a perfectly mixed electrolyte, such that you don't have any concentration gradients that affect your conductivity. And then you end up with this equation that we use in primary and secondary current distribution with a constant conductivity. So next up, the equation for mass conservation are given by this diffusion convection migration equation at the top here, while conservation of current is ensured by the second equation. So you solve both these two equations, one for the concentrations and one for the current density. And for primary and secondary current distribution, as I said, we can make the conductivity constant to give a simplified equation that is independent of the concentration of the ions. At the boundaries, we have boundary conditions for the electrochemical processes described through kinetics expressions or polarization curves. One can have multiple reactions describing anodic and cathodic behavior at each boundary, and COMSOL will then solve for the mixed potential. Growth of films and dissolution of metals can also be included as model variables. At the right, we see a typical polarization curve for nickel, aluminum, bronze, where the total current density can be divided into two reactions, one for the metal dissolution and one for the oxygen reduction, giving a total net zero current of around minus 0.31 volts, which is the open circuit potential for this metal. The loss mechanism in electrochemical modeling can be divided into three categories: primary, secondary, and tertiary. The primary source for loss are ohmic effects, loss due to the resistivity of the electrolyte. Then we move on with the secondary sources that are losses due to the reaction rates at the anode and the cathode being finite. And if you want to include tertiary effects, you can take it into account of the loss due to the transport limitation of species towards the electrolyte electrode interface. So these are the different loss mechanisms that are considered in these interfaces that we have for primary, secondary, and tertiary current densities. When we are working with electrochemistry, there's a few important assumptions that we have to define regarding the formal directions of currents and reactions. So we need to remember that the current direction is positive from the anode to the cathode. So that means that the anode has positive current densities, while cathode has negative current densities. Then we have the activation over potential, and we have a positive potential for anodic reactions and negative over potential for cathodic reactions. For the electrochemical stoichiometry, electrochemical reactions are written in the reductive direction. Negative for oxidized species and positive for reduced species. And these are sort of assumptions that you use to ensure a consistent modeling of your electrochemical problem. When you set up an electrochemical model, it's important to increase the complexity stepwise. So first you will have to consider which kind of electrolyte you have and which species that are important here. You may want to start with the primary and secondary current interface with a constant conductivity just to get started, and then move to a more complex electrolyte model afterwards. You must also consider if the electrode phase is important for the polarization of the system. If the conductivity of the electrodes are much larger than the electrolyte, you might not need to consider the potential drop inside the electrode. And then you can rather represent them with a constant potential boundary condition. For models with porous electrodes, or for example long pipelines, the model potential drop inside the electrode must be considered, because it affects the polarization of the structure. Next, you will need to find out which reactions you have on each surface between the electrode and electrolyte, and you may want to add multiple reactions or an experimental polarization curve that represents all the reactions that you may have extracted from an experiment. The next level will now be to add mass transport, say for example oxygen transport towards the cathode, momentum transfer, heat transfer, or maybe electromagnetic contributions. And COMSOL will help you tackle these multiphysics scenarios. A common question that we get is, which interface should I choose for my model? As you can see, there are quite a few interfaces available when I have the corrosion module. We will go through and show a demo of a model spanning from primary to tertiary currents. But when looking at the electrochemistry part, you can distinguish between tertiary currents and the others by noticing that primary and secondary cathodic protection and current distribution interfaces with BAM assume that you do not solve for ion concentrations in the electrolyte. Then you have some additional interfaces for mass transport and surface species, and at the bottom you have the corrosion deformed geometry interfaces that solves for dissolution or deposition by deforming the geometry or the mesh. So these three interfaces that we have, or three different categories that we have, it's like primary current distribution, where we assume that all reactions are in equilibrium and they are very fast, so we only have geometrical and ohmic effects that are accounted for in the primary current distribution. Then for a secondary current distribution, we account for the kinetics by including the activation over potential and using polarization curves for the current densities. In this case, ohmic, geometrical and kinetic effects are included. In tertiary current distribution, you typically solve the full Nernst-Planck equations for mass and current balance with several species in the electrolyte. Geometrical, ohmic and kinetic and migration and transport effects are included. In the tertiary currents Nernst-Planck interface, you have to choose between a few charge conservation models. And the basic one is, or the most general one is electroneutrality, where you assume local electroneutrality and the sum of charges equals 0. And if you choose the general one, you add your desired species yourself. If you choose water-based electrolyte, the water self-ionization, so H plus and OH minus species, are added by the default. Then you can also neglect the ohmic losses in the electrolyte by choosing the electroanalysis interface. And you can also use a supporting electrolyte by using a constant electrolyte conductivity. Now, then you neglect the influence of ion concentration gradients in the electrolyte. And finally, you can choose Poisson type, and then that is whenever you have local electron neutrality that cannot be assumed in each point. The current density is an important factor in our simulation that, together with the Faraday's law, determine for corrosion the magnitude of the corrosion rates and the rate of evolution in corrosion products, layers or gases. In electrodeposition, you typically look at the current density to determine the metal deposition rate and uniformity of deposition. And in general, in electrochemistry, it shows you the uniformity of reaction and catalyst utilization in electrolysis or in a fuel cell, or the local state of charge depletion and saturation rate in a battery. For a particular model, when you compare current distribution, a primary currents interface will typically give you a linear voltage-current relationship. For secondary currents, the reaction kinetics gives a nonlinear behavior for the voltage-current relationship. And you can see that in the polarization plot above. And for tertiary currents, when you include mass transport effects, it will further change how the current varies as a function of cell potential. So you can sort of say that this has an increased level of complexity for each step here. And each step leads to more computationally or nonlinear models. I will now demonstrate a model called the wire electrode, and you can see it above. There is a anode in the middle, and there are two plate cathodes on the outside, and they support current to the anode. So first we start with primary currents for Ohm's law with primary conditions on the anode and cathode. So that's voltage constraint. And then next we include Butler-Volmer boundary conditions for the current density on the anode. And then finally we add laminar flow and transport of diluted species to include mass transport effects of a species towards the boundary. So let's start COMSOL. When you open COMSOL, it looks like this, and you can use the model wizard to quickly build a model in different space dimensions. So I'm clicking on the model wizard, and I select 3D in this case. And then we select the physics, and from the electrochemistry branch, I select primary current distribution, because that's where I want to get started with this model. And then I move on to select the study, and I select stationary study. And now the user interface is built so that you can see the model builder tree here. This is where all the settings of the model is located. And you also got a ribbon up here, which you can change for the context that you're in. So if you're in geometry mode, you can quickly find the different entities that you want to include in your geometry. But this time I'm going to import the geometry. So I right-click here for import, and I browse for the file or electrode, and I click build selected. Now I can see that this is in meters, so I need to change the units to millimeters for this case. I click build all, and now you see it's millimeters. So this is the geometry that I want to use. Then I can naturally move on to materials. In this case, we're having an electrolyte here, and we also want to simulate flow, so we need fluid flow properties, and we can use water for this. So we go to add material from library, and we can select from built-in, and we can go and find water liquid. So this will add the necessary properties for the water, but we still need to put in the electrolyte conductivity, which is of course dependent on the additives that we have in the fluid. So I'm just using 10 Siemens per meter as a conductivity here. So then I'm finished with the materials, and I can start working on the boundary conditions. So if you right click on primary currents, you can find the different boundary conditions for the different electrolyte phase and electrode phase. In this case, we just have the electrolyte here. We don't compute anything inside the electrodes. So we use electrode surface on outer boundaries. Then I select the two cathodes that we have. So they are on the outside. Then we specify the electrode reaction equilibrium potential, and we're setting that to 0 volts for this case. But depending on different materials and metals that you have, you might want to change this. But it's of course relative to some reference electrode that you want to use. So I'm setting this to 0, and then I'm going to do another electrode surface for the anode that's located inside here. So if we go to wireframe rendering like this, you can see the electrode on the inside, and we can just use the select box to select all of the boundaries that we have. On the top and bottom here, we got symmetry planes, but that is a natural insulation boundary. So you can see you have insulation on all other boundaries now. So here we want to have a external electric potential because this is driven by a potential stat. So I can put in 1.3 volts here. But I want to do a parametric sweep on this. So then I need this to be a parameter. So I can just right click here and create a parameter and call it for E cell. Cell voltage. And that will automatically be added to parameters up here. Then we can go in and put in the electrode reaction. That has an equilibrium potential of 1.2 volts in this case. So now we are sort of ready with the primary conditions, which is the potentials on the boundaries, and we can go on with meshing and click build all, and you can run a simulation like this just to compute it. It's quite quick, it's a small model, and you can see the potential. So now since we have 0.3 volts on as a cell voltage, and the equilibrium potential is 1.2 volts on the anode, there is a potential difference in the electrolyte of 0.1 volts.
The advantage of using auxiliary sweep is that it uses the previous solution as the initial value for the next solution. And that can be quite important when you work with very nonlinear problems such as in electrochemistry. Also in auxiliary sweep, you can only use parameters that are not changing the geometry or changing the mesh, but it's okay to change boundary conditions and variables in the physics.
So I go to the solver, and then I can use this study extension, auxiliary sweep, where I can add eCell as a parameter just by clicking this plus. If you have several parameters, you can choose in a list from this. And then type range 1.25, 0.05 to 1.8 volts. And we compute it over again. It's fairly quick. And we can look at the electrolyte potential, the current densities at different potentials, and so on. But what I'm interested in here is the total current that goes in the between the anode and the cathodes. So I want to do a 1D plot group, and I do a global plot. And here I can find some electrode kinetics, total current, and ES2. So this is the electrode surface 2 has this subscript here, ES2. You can actually also change the tags. So if you click up here in this list and choose tags, you can see that you get this ES2 tag. And this is also useful later on. So we can plot this, and we can see that we have a total current that is in a linear relationship, just as expected for a primary current distribution. And now I just want to copy the solution before we move on to the next step, which is secondary currents. So I just right click on the solution and select copy. And now we get this solution copy, and I can solution 1 primary like this. Now I can select this solution down here in this node just to make it easier to see, and we change the legend to primary like this. Okay, so now we are ready to work on with the secondary currents. So then I go to the primary current distribution and I select current distribution type secondary. And when I do that, it changes the boundary conditions. So now if you go to the electrode reaction, you can see that I get this kinetics expression. And here I want to change the linear to Butler-Volmer instead. And I do that also in this electrode surface here. Change this to Butler-Volmer. Of course, I can change the coefficients here, but this is just to show how these exponential equations affects the total current in the model and also the computing time. So now I've changed this to secondary with Butler-Volmer, and we can just go on, compute that. You can see it took slightly longer to compute. And we can also just copy the solution now, just to make it with secondary. And yeah, you can do the same thing, look at the current densities and so on. And you can also go down here. If I want to look at the difference in total currents, duplicate this, select primary, secondary. And now it's on the same solution, so I need to change this solution data set up here. So I select solution 1 secondary. And now you can see that including the activation over potential and the Butler-Volmer equation, it affects the total solution. And the next step now will be to add the tertiary current step. So then I right click on the component one here and I click add physics. And now I want to add fluid flow. So I go with single phase flow, laminar flow. And I also want to add transport of diluted species. So we have a species here that is injected and then it's consumed on the anode boundaries. So first we will set up the laminar flow, and here I select inlet, and we can type in that's 5 millimeters per second. This, and then we can make an outlet the other side. And since these two boundaries are symmetry boundaries, we can add a symmetry boundary on the top and on the bottom like this. So then I'm done with configuring the fluid flow physics. And then we move on to the transport of diluted species. So here we can see that we can add the transport mechanisms. So I want to add migration in electric field. And I also want to have a look at the dependent variables down here. So you can see you have one dependent variable, which is my concentration C. And then I can go in and define the species charge. So that should be 1 in this case. And also we can look at the transport properties. And you see that there is an empty 0 here for convection term and the electric potential. So if you want to couple this to the secondary currents and the fluid flow, you go to the multiphysics node and select reacting flow. So here you couple laminar flow with transport of diluted species, and you want to go do a potential coupling in this domain of secondary currents to transport. So if we go back to the transport properties now, you can see that these are grayed out and coupled to the correct field. So that's what this multiphysics coupling does. And then I can right click here on transport and add an inflow. So that's concentration. And we use 1000 mole per cubic meters here. And for me, it's useful to have this as a parameter as well. So I create a parameter C in. And then we define an outflow on the outlet boundary. And then for the anode, we want to have a surface reaction. So here we have this electrode surface coupling. And here we can select the boundaries of the anode. This. And we go to reaction coefficients. So here we want to couple to one reaction. So I want to couple to this ES2 ER1, which is the anode reaction. And we have one electron and it's reduced on the anode boundary. So then the stoichiometric coefficient is 1. So now we have sort of coupled secondary currents into the transport of diluted species so that the diluted species is consumed. But we also want this to affect the electrode reaction that happens up here. So we need to go to the electrode reaction Here we can change the equilibrium potential to be of the Nernst equation. So here we have a reference equilibrium potential, and you can see that you have this log relationship for the concentrations. So here we type C divided by C in, so it's normalized. And now when the concentration is changed on the boundary, it will affect the equilibrium potential. And we also have the same type here for the Butler-Volmer equation, which now takes these things or these expressions from the equilibrium potential and puts it into the equation for the current density, like this. So we need to change this to be the same as the initial current density. And now we can compute this because we have set up all the bidirectional couplings. One nice thing about this is that the fluid flow doesn't affect or the transport of the diluted species doesn't affect the fluid flow. So we can compute the laminar flow first, and then we compute the secondary current distribution afterwards. So we add a new study. Click add study here, and I select stationary, and then I want to just compute the laminar flow first. Let's just add this. So here we see the stationary, and then I can add another study step in the same study. So I add a stationary, this, where I do not compute the laminar flow. And if you do this, it will automatically take the initial values from the fluid flow and put it into the second study where you compute the secondary and transport. So now we can get the default solver because I want to change this slightly. It's a very small model, so there's no need to use advanced 3D solvers here. So I can go in and look at the stationary study. So here we have the first one, stationary solver, and there's the second one. So we can go in here and just select a fully coupled solver and use a direct solver on that. So that's one thing, and then we need to add this study extension that we had. So we use this E-cell range 1.25, 0.05, 0.8. Now I'm ready to compute. And this typically takes a couple of minutes. We can look at the convergence plots. You can see this is the nonlinear solver, and that is solving now for the fluid flow. So it's running the stationary solver 1, and it has converged with the fluid flow. And then it starts to compute the transport of diluted species and electrochemistry in a new nonlinear solver. So it took 3.5 minutes to compute all these solutions, and we can now look at the first this total current. So let's just duplicate this and select solution 1, solution 4, and we need to change the legend so that it says tertiary. And you can see that it has changed the total current for larger potentials. You get the transport limitation due to the diffusion and convection. So it cannot supply enough of the species to sustain this current density that you had here. So if we look at the velocity, you can see the velocity flow here. Let's change this slice to be of XY plane and one plane. So you can see it here, how the convection looks like. And you can look at the concentration on the surfaces. So let's just make a selection on the surface plot here so that we can all boundaries except these. Maybe we can remove this outer boundary as well. So you can see how the concentration changes and change quite a lot because a lot is consumed on the first part here. We can also add a slice plot. So that's the concentration C. We want the XY plane, one plane. And it's beneficial to use inherit style in this. So we inherit from surface 1, so you get it in a common scale. So now you can see the concentrations in the flow. So this is the reason why you get a lower current density for high cell voltages, because you have a lot that is consumed and less that is transported towards the surfaces. But if we look at 1.25, you can see that there is a lot more of the species that manage to diffuse towards the other surfaces. So that's how this tutorial works. And you can find this tutorial if you go to the application libraries. So there are sort of two major factors that drives the computation time and the memory consumption in a model like this, and that's the size of the model, like the physical size, and the complexity. So that's sort of the number of species and the nonlinearities you have in your boundary conditions. So for a large offshore or jacket structure, you typically have a very complex geometry, which with a lot of small pieces and large pieces, and that creates usually quite large meshes, which require quite a lot of RAM and CPU power to compute. And the next opposite thing would be species concentrations in a corroding crevice, where the crevice is just a couple of millimeters long, and you can do a 1D simulation of it, but you want to include 8 or 9, maybe more species in order to get a correct overview of the chemistry inside the crevice. And that also adds a lot of complexity and especially nonlinearity to the equation, which require RAM and power and time to compute. So there's always this trade-off between doing a large model. You might want to simplify your equations a bit and not take all the details into account. So you do some assumptions, maybe that you have a constant connectivity in the electrolyte, or you assume that you are working in a range where you have enough oxygen to sustain the oxygen reduction reaction and so on.
Of course, you can combine this, but then you might want to reduce the geometric complexity of your model. So these are two major things to be mindful about when you build your own corrosion models.